knows a lot about the science stuff. Professor Dave explains.
In the previous tutorial, we discussed the importance of ethylene polymerization. The ziegler-natta process launched the plastic industry and represents one of the most important chemical innovations of the 20th century, as well as one of the first large-scale applications of homogeneous transition metal catalysis. In that tutorial, we also discussed an incident in which the polymerization using the titanium-aluminum catalytic system did not work at all, as the reaction stopped at an oligomerization stage, forming alpha-olefin products like 1-butene, 1-hexene, and higher homologs. The problem was attributed to trace contamination of nickel metal. Once nickel was removed, the polymerization worked again. This implies an early termination by beta elimination of an MH species, carried out by the nickel contaminant. You may have wondered whether oligomerization of ethylene could also be a useful process, given that lower alpha olefins are not abundant in nature. The process would look like this for the dimerization of ethylene, where the metal M is still to be defined. As we can see, an MH species would undergo coordination of ethylene, followed by hydrometallation, or addition of the MH species to ethylene. Further ethylene coordination should be followed by carbometallation, or insertion of the MC bond across the ethylene double bond. This insertion of ethylene into the growing alkyl chain can be repeated many times, and at some point termination occurs by beta elimination, regenerating the MH catalyst and forming the alpha olefin. The oligomerization of ethylene using nickel catalysts has indeed become a reaction of great importance. Every year, over 1 million tons of alpha olefins are produced by what is known as the shop process, which was first discovered in 1968 at the Shell Research Group in Emeryville, California. It was commercialized in 1977. In the 1960s, Shell and other chemical companies searched for an efficient process to prepare long-chain alpha olefins in the range C12 to C18. Which were substrates for hydroformylation, leading to detergents, which need to have long enough chains to form micelles. Hydroformylation is a process we introduced earlier in this series, so go back to that tutorial if you need to refresh your memory. The Shell Group drew inspiration from the ziegler-natta process and endeavored to find a homogeneous nickel catalyst which would lead to long-chain terminal olefins. After screening many ligands and a nickel zero source, they hit the jackpot with alpha-diphenylphosphinoacetic acid. The catalyst was formed by interaction of nickel bis-cyclooctadiene, or NiCod2, and alpha-diphenylphosphinoacetic acid. This produced alpha olefins with what is called a Flory-Schulz distribution. 1-butene, 1-hexene, and 1-octene were major products, with the desired fraction C12 to C18 constituting about 40% of the entire mixture. Distillation afforded the desired fraction in modest yield. For the process to be effective, the yield of the desired fraction had to be improved, and therefore the shop process includes 2 extra steps to reutilize the low and high molecular weight fractions. The second step is a heterogeneous catalytic step over an aluminum catalyst at high temperature to bring about isomerization of the terminal olefins to internal olefins. For example, 1-octene is isomerized to a mixture rich in 4-octene. The final step is an olefin metathesis reaction using a heterogeneous catalyst based on molybdenum. This combines long and short olefins to produce olefins of an intermediate length. For example, 4-octene with 8 carbons and 10-icosene with 20 carbons combine to form 2 molecules of 1-tetradecene with 14 carbons, which is the desired length for the hydroformylation reaction. At each pass of isomerization and metathesis, 10 to 15% of the unwanted fractions are converted to useful products, rendering the process more efficient. We will deal with metathesis reactions later in the series. It was also found that using a polar solvent for the reaction, 1,4-butane-diol, the olefin products were immiscible and floated on the solvent layer containing the catalyst. This made separation of the product trivial and recycling of the catalyst easy, achieving excellent turnover numbers. The mechanism of the reaction was elucidated by German chemist Wilhelm Keim, who had been part of the Shell team, and in 1973 had returned to Germany to take a professorship at RWTH in Aachen, Germany. The catalyst itself is formed from the precatalyst NiCod2 and phosphine in the presence of ethylene. The nickel 0 species coordinates to the strong ligand, the phosphine, which expels one molecule of COD from the coordination sphere of nickel. The next step can be seen as an oxidative addition of the OH bond of the ligand to the nickel 0 species, resulting in an oxidation of nickel 0 to nickel 2, the active oxidation state. In the presence of COD, the nickel 2 catalyst can undergo hydrometallation with COD to produce off-cycle species A, which is not productive and is at equilibrium with the active NiH species. This can undergo fast ethylene hydrometallation and successive carbometylations, as we discussed. The timing of the beta elimination depends on the reaction conditions and can be fine-tuned to some extent. The SHOP process is still being researched and newer ligands sought in order to obtain a more narrow distribution. More recently, chromium catalysts have been discovered at Chevron, which produce 1-hexene or 1-octene in over 70% selectivity. This has been the result of extensive metal and ligand screening. We will not discuss these developments in detail, except to note that the mechanism is not identical to the one we just described, and therefore represents a special topic. The chemical company Sasol has commercialized its 1-octene process to hundreds of thousands of tons of production per year. Overall, about 1 million tons of 1-octene are produced each year by tetramerization of ethylene, which is largely used as co-monomers in the ziegler-natta polymerization of ethylene, leading to new plastic materials. Current intensive research in the ethylene oligomerization area revolves around improving selectivities in alpha olefin production, and given the industrial importance of the olefin products, one can be sure of continuous breakthroughs.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.